Okay, so today we are going to kind of go over some material. So we're starting, I think it's chapter 4, starting the chapter on forces and Newton's law. So I want to go through that stuff. I want to answer some questions that people might have about the homework that's due tonight, and make sure everybody's feeling okay about that. Next Tuesday, we're going to have our second exam, and it will cover 2D kinematics, and really it's all kinematics. It could have some 1D stuff as well. That's how physics courses tend to be. They build and build and build. Nothing really goes away. So that will be online like the last one, where I will post it at, I think 8 a.m. is when I did the last one. So I'll post it at 8 a.m. It'll be due by the evening. Do you remember when I, 12 midnight? Yeah. Okay. So I'll do the same thing. So that's how that will go. It will be a mix. I haven't written it yet, but it'll be a mix of conceptual and quantitative stuff. So kind of like the last one, but it'll be just a mix of things. So that'll be next Tuesday. It will cover kinematics, which means nothing that I talked about for those of you who came or logged on for the Zoom meeting on Tuesday or today. It won't cover the stuff we're doing this week. It's just on stuff that was due up through last Friday. Okay, so anything up through last Friday on sapling is fair game, not the stuff for this week. Okay. Other questions about that? So like last time, I want you to download it, print it, do the exam, upload it. I think the easiest way, I mean, who in here's pretty cool and awesome? Apple iPhones, anybody have an iPhone? I'll see. So there are a number of really cool, awesome people. I don't know about the others. You figure it out, Charles. No, at least on here, if I go through the note application, if I click on the camera icon, one of the options is to scan a document, and you can just do kind of page after page after page after page, and it stitches them together as one PDF file. So that's kind of a handy way to do it. Question? He's wishing he had a better phone. See if it makes you a better person, makes you funnier. Yeah, you have better jokes at parties. No. Okay. All right. Questions about that? I don't think. I won't be. I mean, I'm sure sometimes it feels like it. Maybe I hope not. But I'm not trying to trick people, and that would not be my intention. So if there's a problem, let me know. I'll do the same thing as before. I'll go ahead and be available at 10 on that day. So if you print it out in the morning, look at it. If there's something that seems like, maybe make an attempt at all the questions, just kind of see if you can do them. If there's something that's confusing, let me know, and I can try to answer questions. So I'll be available during that time block. Because I mean, I wouldn't want to trip you guys up because I'm being sneaky. I would rather do it honestly, just really make a really impossible question. No, that's not my purpose, and that would not be something I would try to do. I'm not trying to trick people. So if it doesn't make sense when you read it, it's probably because I wrote that question. It's no deeper than that. So if you have a question, I'd want you to ask me. Okay. Sapling. I asked some of you earlier. How many of you guys were able to start or or at least look at the sapling for tonight. Okay, so there's sapling for tonight. It's on forces. It's should be a pretty straightforward one, but I want to take some time at the very end to make sure everyone is okay before I send you guys out the door. The last few questions are on Newton's third law. We're going to talk about that during class. So after that, should be easy. The last two on Newton's third law are conceptual, if I remember right, they're like 5-minute questions. They're really fast once you understand what to do. They're not long. Okay. All right. So let's begin. So we're talking about forces. Hopefully looked in the chapter 4. Or the other thing I did, I saved the kind of where I was writing, and I uploaded a PDF of that to Blackboard. So if you weren't able to log on Tuesday, you could see everything we did. There's a record of it. Basically, I worked one problem, I think, in detail, maybe a couple problems in detail. So kind of show you what I'm doing. What is a force? What is a force? Star Wars? No. When we say force. So a force is a push or a pull. So it's any sort of phenomenon that generates a push or a pull. So a push or a pull is what we mean by force, and let's write that down. Okay. There are a number of common forces. Like right now, are you guys feeling any forces right now? Is anything pushing on you? What's pushing on you? Okay, I suppose I would usually think of that as a pull, but no, it doesn't really matter, right? Something else is pushing on you guys all right now. The air, right? There is, right? Air. There's air pressure, which a pressure is force per unit area. So there's a force being exerted on us. Although pretty much, since I have air pressure on me from all directions, pretty much the air pressure averages out to about 0 in terms of force. The pressure's there, but some of it kind of is going down, some's kind of going up, and it averages out. There is a little bit of a net force from air, though. There's a small buoyancy force, like when you put a ball in the water, there's a buoyancy force. You actually have that same effect anytime you have a fluid. So air is a fluid, so there would be a small buoyancy force going up. I don't know what it would be. It'd be a small number, though. So small that I don't notice it. Okay. Anything else? So here's the thing. To figure out if something's acting on you, imagine you were to use the magic wand of physics and make it disappear. Is there anything that I could blip out of existence right now and it would significantly affect you? What about your chair? Right? If I were to blip the chair underneath you out of existence, you would notice, right? Okay, the chair is exerting a force on you as well. Okay, so those are all forces. There are different kinds of forces. I went through this on Tuesday a little bit, but there are contact forces, and then there are other ones which are non-contact forces. Is that okay? Can you read that, or is it clear enough?
Yeah, that's good. I can read it.
Non-contact forces. So there are two kinds. I could have asked Gavin, but tough luck, Gavin. All right, contact forces mean what you think they mean. Non-contact. So, I don't know. I usually ask if somebody's got a sibling. Anyone have a younger sibling, older sibling? Yeah. Right. So, you punch your sibling. Right. That's a contact interaction. Okay. And that would actually be a norm. We call that a normal force because it would be perpendicular to the surface of contact, your fist. Non-contact. So that's like movie punches or something. There's no physical connection between the objects. All right. Examples of contact forces are, well, the chair pushing on you. Which way is the surface of the chair? It's flat, it's horizontal. Which way is the force it exerts? Perpendicular to that, so it's going straight up. Right? If I push on the wall, okay, the wall is vertical. Which way is the force it exerts on me? Perpendicular. Okay? So in math class, the one way to say perpendiculars is the word normal. In math, normal means perpendicular in many contexts. Who's heard of that term before? Few people. Right? So another way to say this is orthogonal, but we will use the word normal. So a really important force for us will be normal forces. A normal force. A normal force is perpendicular. Let's write that. Perpendicular, is that okay? Sounds right up. Perpendicular. So it was the force perpendicular to a surface of contact. Conversely, if two things touch, you should assume there is a normal force. And then, maybe you solve the math, you solve the problem, you do the math, maybe it turns out that it happened to be zero, so be it. But when in doubt, if two things are touching, assume there is a normal force, and then if the arithmetic tells you that it actually happened to be zero, fine. But any sort of contact, assume there's a normal force. Normal means perpendicular to the surface. So, oh shoot, I glued that down in the train. Not gonna work. Okay, so I've got a table. And I've got a stapler. Okay, so right now, the surface is horizontal, and the normal force is perpendicular to that, so the normal force points straight up. And we do a lot of problems like this. So people get used to that. And then pretty soon, after a week, they start thinking that all normal forces point straight up. That isn't right. Okay, so if I tip it to, I don't know, 30 degrees or so, and whatever, okay? Now, the surface points this way. Which way does the normal force go? That way, right? So the normal force will follow the surface. Okay, so when we get to, maybe today, we solve problems where you have blocks and things moving on hillsides, the normal force has a direction which is determined by the surface, not gravity. So, all right. Perpendicular to the surface of contact so that as you change the surface, the normal force will change. Force. Another one we'll deal a lot with ropes, chains, wires, those kind of things, okay? Those all generate what's called a tension force. Okay, so this is force from rope, wire, chain, anything else I can't think of. And this will point along, it's a force that will pull along the string, there you go. It points along the object. It points along the item. Okay, so if I have a rope and I pull it, simulate a rope with markers. Okay, so if I pull a rope, the direction of the force it would generate would be along the body of the item. So the angle, again, is determined by the problem. You have to look at the picture, read the problem, determine those things as you go through. I should have said this. I will try to consistently use the same symbol. And when I do this, every time I have a normal force, I will write that as in, and if I'm really being careful, I'll put an arrow over it. And when I have a tension, I will use a capital T. Not to be confused with period, which also has a capital T. They're different things, they're different units. But that's just what I do. Did anyone do something else in high school? Anyone write like a capital F for force with a subscript? Totally fine. I would suggest do whatever seems natural to you and then do it the same every time. This stuff isn't rocket science. There's no use wasting brain cells reinventing the wheel. So come up with a routine, come up with a system that works for you so that you can consistently work your way through things. Okay, don't waste time making up a procedure. Okay. Normal force, tension force, we'll have friction. So this is a force which opposes motion. This is a contact force which opposes motion. The symbol I would use for that is kind of a script kind of F. I think that's what the book uses. We're going to have different cases. So it's when things are, more precisely, this is dry friction. So this is friction when you have dry objects being pulled along each other. Okay. Engineers, mechanical engineers have to learn about dry friction, wet friction. So that's like when you get water or oil there. More elaborate concepts. We will have very simple ones. We will have two cases when things, before things move or after things move. Okay? But that's a little bit more complicated. So this will be, after we get pretty good at dealing with just generic or simple forces, then we'll build up to this. Friction. We'll have forces from springs. When we talk about the force due to a spring, that I'll probably just write as F, something like that. Okay. Force from springs. Again, that one is a little bit more complicated, and so that'll be one of the later ones we introduce after we're pretty good with dealing. Tension, friction, springs. Other, I guess maybe the final one that I can think of here is drag force. And I will just write that as D, the vector. Drag force, morally speaking, it's a type of friction. It's a friction between, like, drag, so that's like wind resistance when I'm moving around. It's a friction between me and the fluid, the air around me. But because the formula and the way you handle it is so different than sliding friction or kind of dry friction, we just give it its own name, just so we just clearly separate things, even though it really is about the same. Did it ever synchronize? No. That clock is broke. All right. It's kind of our laundry list of forces. Are there any other forces that we think are relevant for this room? You have any ideas? Any ideas? It's another one that might be important. What about gravity? Gravity is a big one that we haven't mentioned. Gravity is a little different. These all require some sort of contact. And I know drag force, that's contact between a fluid and an object, some sort of physical connection. As far as non-contact forces, there's gravity. This is between two objects. I should say this one pulls two objects together. Okay. So if I step out of an aeroplane and I'm in free fall, the force of gravity is pulling me towards the center of the earth. It turns out it also is pulling the earth towards me. It'll turn out to be an equal size force, just in the opposite direction. Now, the acceleration or the motion that is caused isn't symmetric. The force is symmetric. The force of the earth on me mirrors the force of me on the earth. There's a symmetry there. The emotions clearly aren't the same because, right? I fall down. When I did that, did you guys feel jerked upwards? Did the earth move? No. So the motions don't have to be symmetric, even though the forces are. Okay. We will also have electric, magnetic, and then there are these actually, although it's not clear, these are actually different manifestations of the same thing in a kind of tricky way. They're actually the same. What other forces do we have? Have you heard about them in chemistry classes? They're nuclear forces. We call it, what do we call them? Strong and weak nuclear forces. Okay, so there's the strong nuclear force and the weak nuclear force. The weak nuclear force is what causes a lot of radioactivity, beta particles, alpha particles, things like that. The strong nuclear force is what binds together quarks inside of a proton or neutron. So I'll just call those nuclear forces. Okay. It turns out there are two of these. It turns out these are the fundamental forces of nature. So at some level, these are actually the only thing that's real. All these up here are effective forces. And in reality, they're mostly just electromagnetic forces in different situations, they behave in different ways. So if you were to talk to an atom, they wouldn't know about friction and drag force, spring forces, ropes. They wouldn't know about any of that. They would only know about these fundamental forces, and mostly they would care about electromagnetic forces. It just turns out that when you put atoms together in certain contexts, these are good, effective descriptions for the everyday reality that we experience. These are the fundamental ones. Okay. All right. Very good. In this class, we will not worry about these. This is the one that we will care about. Gravity. Another name, I should say that, another name for gravity, same as weight. Weight is just another name for the force of gravity. When there's a problem that's on the Earth's surface, in this situation, we pretty much use everyday language, and so we say weight. If there's a problem about space, or whatever, then we will say force of gravity. But really, they're the same thing. Just manifestations. Other questions about those? All right. It's kind of a laundry list. What I want to do now or next is kind of run through how you the connection between forces and motion, and which is going to introduce the concept of Newton's laws. And so we're going to go through those, and then we're going to just start using those to solve some simple problems. That's kind of the plan. Okay. All right. So the connection, so what we have to develop next and run through is the connection between forces and the motions around us. So Newton deduced 3 laws of motion. Actually, did more than that. There's a 4th one, which is his law of universal gravitation, which is, specific to gravity. But the 3 laws of motion apply to any force in any situation and any object. So they're very universal. So that's what we talk about. Why we highlight them. So we have the first law. What does the first law say? Anyone know? Just so not for Monday or for Tuesday's test, but when we have our test on forces, I will want you to be able to state Newton's laws. Now, I don't mean, I'm not too worried about preposition, like did you get the right comma and the right preposition? I mean, can you state in general terms accurately what the laws of motion are? Because it's a big deal, right? Anytime you can make a statement which describes everything in the universe, that's a big deal. So you should be able to say it. Okay. So if no net force acts on an object, then if the object is at rest, or if initially at rest, then it remains at rest. Okay? B, if initially in motion, then it continues. Usually people say in straight line motion at a constant speed, but we can just say continues with a constant velocity. Continues. With the same velocity. All right? So let's see if we can set this up. I'm going to hand out a card. I want you to look at what happens. Don't throw this at your neighbor, even if you want to. So, okay. So what I want you to do is push the cards. Actually, first of all, we're going to do a very important experiment. Okay? Very important experiment. Ready? Uh-oh. Okay. Here we go. Ready? I mean, this is a high point of human achievement right here, right? There are three of these laws. Right? So if this is a movie, there would be like at a crescendo, right? The music's blaring. Ready to see it in action. Ready, go. It's pretty impressive, huh? That's it, right? That's a pinnacle of human achievement right there. Okay. There's no net force. What does net mean, first of all? I should have spelled that out. Net. So if I asked about your net income, what does that mean? Total. So that means you add in gains and losses after tax. Okay, your gross income would be just the plus side, plus numbers. Okay, net income would be gains and losses. That's what we mean. So in this case, we're not talking about gains and losses of money. We're meaning you add, I mean that literally, add the vectors as vectors. So if you have a vector to the right and a vector to the left, they cancel out. Okay. So in this situation, what are the forces that are relevant for this card? Let's go through our laundry list. What are the ones that seem to be acting on this? Gravity, yeah, it's on Earth. If there's a problem on Earth, pro tip, during the Southland question, they just start talking about tables and chairs and things, you can assume that's on Earth, okay? You don't have to assume it's in space or anything. All right. Gravity. We're on Earth, there's going to be gravity. Yes. Anything else? Yes?
Don't you have like normal force?
A normal force, yeah. So there's got a flat surface, there's a contact. If you see contact, assume that there's a force there. So it's at rest, evidently, just as an observation, those two forces add up to zero because it is remaining at rest. So those two forces cancel out. I'm doing nothing in the horizontal direction. So all the forces add up to zero. It started at rest. Therefore, it remains at rest. Pretty impressive. Right? That's case A. All right. Now, for B, it could be that we just, hey, get those Nobel Prizes ready, right? I did nothing and it started to move on its own, spontaneously. Maybe Newton's laws don't hold. Or what's the other possibility? The table's not level. The table's not level. But, all right, Now, if I start this out moving, what would Newton's law say? And in what kind of motion? Will it make like a serpentine pattern? No. Straight line motion. And because constant velocity would be neither the direction nor the speed changes. Everything's constant. So that means straight line, constant speed. So if I started out moving, ignoring the tilt of the table, I should get constant velocity in a straight line. All right, this seems plausible to my eye. All right, so take a second, push your cart along your table, see if you get the same kind of effect. I gave you the bad one. We were doing experiments with friction the other day, so maybe there's friction. Turn it over. See if there's something taped to the bottom. There might be something taped there. No? All right. All right. Your guys' carts continue with a constant velocity after you set it in motion. Really? If you had constant velocity, they all would have just kept on going off the table. Nobody's cart went off the table. So what do we conclude? Well, since it didn't, I mean, it sort of looked like constant velocity, but not really. We conclude that the initial assumption wasn't quite right. There must have been some other force invalidating this. That was friction. There's always a little bit of friction. So as part of Newton's genius was to imagine a world with no friction. And I don't think, my understanding is that when he was thinking about all this stuff, many of the pieces had been mentioned by different people, but I don't believe it had been pulled together in one consistent package. So, like for this one, I think other people had discussed this idea, although I would say most of the kind of really sharp people up to that point had not thought that this is what would happen. Most other people thought that there was something like, what do they call it? I cannot remember what it was called. Anyways, the idea was that things want, in quotes, to be at rest. That was a common assumption. So if you read Aristotle, there's this notion of things, there's a preferred condition of being, and that is that things are stationary. And the reason that was a not unreasonable thing is because if I throw something and I wait long enough, it comes to rest, right? So maybe it's just a law of nature that things want to be at rest. So Newton kind of turns that around and says, no. If anything, things want to just keep on trucking, keep on moving with no change to their velocity. The reason why in our experience things are always coming to a rest is because we live in a friction-dominated world. So yeah, you have to be able to imagine a world without friction to kind of see that. Okay? Now, let's see. I bet that I can arrange and minimize friction so much that I can push somebody the length of the hallway. Push them and just let it slide, or just go to the other end of the hallway. Anybody believe me? Cool. All right. Now I can. Can you do that? I could probably do it with one hand. You want to see this feat? This amazing thing? Throw someone all the way down the hallway with one push. All right, let's go do it. Yeah, we're gonna do it right now. All right, people online, stay with us, hopefully. I'm gonna throw somebody down the hallway. It's a feat of superhuman strength, the most amazing thing you'll see today. All right, we're gonna put these people here. All right, kind of spread out. Okay, I'll tell you what. Oh yeah, shoot, I can't have you guys touch each other. All right, everybody spread out. Here we go. All right. Would you be volunteer?
Yeah.
Well, I didn't say I was gonna poke that. So what this is a little hovercraft. And when I inflate it, the board is up just a little bit, and it actually does drag, so there is a little friction, but it vastly reduces the friction. And then you can see that more or less the person just travels at a constant velocity the length of the hallway after we get them moving. So it demonstrates Newton's first law. Okay. Why don't you guys come behind? Because it would, I mean, there's foam around the edge, but if it did hit your foot, it probably wouldn't. So this is like a super skateboard. So if you step on a skateboard, it might roll away from you. This definitely will. Okay, so we can't do that. What I need for you to do is just to sit and crouch next to it. Let me inflate it first. And then if you crawl on it and sit right in the middle, kind of on the bolt, then it'll balance. If you get on the edges, it drags. So, but whatever you do, don't try to step on it. Sometimes people try to do that. So once it's going, you'll have to hold this up, and then there's a little switch. Just push it over. Turn it off. All right. So if you go ahead and crouch down. Okay. All right, here we go. So pretty much constant velocity. Oh. So you turn it off. So pretty much straight line motion, constant velocity. If we had no friction, it would, in principle, go forever. Okay. Does anyone else want to try? No one? Supply? All right, you guys are a tough crowd.
You want the class?
What's that?
You want the class?
Oh, I'll bring it back. Make them sit in the hallway and think about what they've done. Excuse me. Okay. All right, so, and that's the sort of scenario that I think in Newton's time would be much harder to imagine because they didn't have air hockey, they didn't have spaceships, and it's hard to imagine that situation. You guys have the advantage of actually being able to see some of these scenarios. Okay. All right, so that's Newton's first law. If there's no force, no net force acting on something, it just keeps on moving with the same velocity. And if I say it that way, it actually covers both cases because you just say the first velocity was zero. It just stays zero. All right. What about Newton's second law? let's see here. So what I want you to do, so the first law is kind of what happens when you don't act on the cart or the object. What happens, or what do you have to do to make the cart move? Make your cart move. So everybody has a cart in front of them? Make it move. All right, it works the same. All right, what do you have to do to make it move? Okay, how about what do you have to do? Let's say it's moving with a velocity. What do you have to do while it's moving? So it starts out moving, and I said, okay, I want you to increase the velocity. What do you have to do? I have to hit it again, right? Because we already said, if I don't hit it, what do we know about the velocity? If I don't do anything, the velocity will remain constant. So if I want to increase the velocity, I better not do nothing. I better do something. Well, the only thing I can do is exert a force. So here's the thing. People talk about forces a lot of times. Even after they know Newton's laws, they will talk about it as if forces are required for motion. Not true. You were moving down the hallway long after, I wasn't affecting you. So force is not required for motion. Not at all. Force is required to change the motion. Forces are associated not with velocity, but what? What's the concept that measures, or the quantity which measures changes in velocity? Acceleration. So forces govern acceleration, not velocity. Okay? I'll say that again. Forces are not required for motion. Forces are required for changes in motion. Okay. So this car's moving. If I want to make it move faster, I better push it. I better do something to change its condition of motion. Okay. All right. So the second law. So I'm going to say it in kind of a. So the idea is going to be that forces cause changes in velocity. Okay? So forces cause changes in velocity, and I really should say it's going to turn out to be net forces, okay, that are going to do that. It's a little trickier than that, because if you exert the same force on a marble and a bowling ball, do you get the same motion? The same acceleration if you push equally hard on a marble and a bowling ball? No, you don't get the same effect. So, I want to hand out some weights, some masses. So you can load up your cart. You can load up your cart. And what I want you to do, I tell you what, you really need to work with a partner on this. What I want you to do, I want you to take one finger, hold out your finger, not that finger. All right, one finger. And what I want you to do is have your eyes closed, and you're going to push the cart. Okay? The person, and I want you to do your best to make the pressure, the force, feel the same. Once with the mass, once without the mass. And the other person will watch the motion that it causes, and then you'll switch. You can see the effect. Okay? All right, so take turns. So when you push, just figure it out, whatever. All right? Just, if you watch them and they'll watch you or whatever. Or at the back, you guys can go together. All right. Okay? So just figure out who's going to go first. you kind of have to close your eyes because that sort of keeps you honest so that you're focused on the sensation, the force. We have this tendency when we watch things to kind of adjust to make the outcome whatever we want it to be. So by not looking, it limits our ability to cheat. For people online, I will do this. Okay? So I'm going to push this with my hand, or sorry, with no mass, and then I'll do it with a mass. And I probably need something to stop it. All right. You guys use these anymore in chemistry? CRC reference book? No? All right. When I took chemistry, we didn't have the internet, so if you wanted any number for a chemistry property, you had to look them all up in books like this. All right, here we go. So I'm going to push this with my eyes closed. I'm going to try to make the pressure or the force seem the same. Okay, so there's that. Okay, I'm going to try to make it feel the same. What do you notice? When you increase the mass, how big was the change in velocity? If I make the mass bigger, for the same amount of force, do I get as much change in velocity or do I get less? Get less. Okay? For the same amount of force, if you increase the mass, the acceleration will be smaller. So forces masses, or mass, reduces the change in velocity. Mass of the object. What is another, maybe a slightly older word for mass? Begins with an I, ends in an A. Inertia? You ever heard that term used? What does inert mean? Again, noble gases, right? In chemistry. So inertia, sometimes this is called, anyways, there's a principle of inertia, which should actually be the first one. But basically, mass governs the resistance to changes in velocity. That's how you measure mass. That's one way to measure masses of things. So one of the So assume I didn't know that what I just did. I have two cups with different masses inside them, okay? But if I try to shape them, right? A shape, that's not constant velocity, so that's accelerated motion. Acceleration, 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 right? This one is much harder to accelerate. It's much harder to shape this one back and forth. No wonder it has a much bigger mass than the other one. Okay? So I used to have, looks like it got thrown out over the summer. Unfortunate. Maybe I'll bring it in. If I can remember, I'll bring it next time we meet in person. I had a bottle of Diet Coke or Pepsi and regular Pepsi or Coke, whatever. And it turns out that the artificial sweetener is actually tastes much sweeter per gram than sugar does on our tongue. So therefore, they don't put as much in. So they have to add less artificial sweetener to each bottle than they do real sugar. Consequently, even though they have the same volume, the mass of diet soda is less than the mass of regular soda. And it is enough that if you put both, again, you have to do it with your eyes closed, because if I tell you the answer and you're looking, you can make it feel how you think it should be. Your brain can trick yourself. But what I usually do is have people close their eyes, and I have the bottles behind my back, and then I give them the bottles, and and you do it in each hand. You kind of shake your hands back and forth, and then you switch, and you switch. And what will happen is you can feel that one of them is just a little bit harder to shake. And that's the one with real sugar versus diet. You can really feel the difference. But it's close enough that if you know the answer, you can talk yourself into it. It's that sort of thing. Also, if anyone plays baseball or does bowling, they can't do it because they have one arm that's much stronger than the other, and they can't feel the difference easily. So, anyway, try that maybe over the weekend if you are looking for something to do. Okay, so forces cause changes in velocity. That's acceleration. Changes in velocity. That's the thing that we know about that measures that. Masses reduce the change in velocity, or reduce the size of the acceleration. So what we're left with is the following formula. The acceleration of an object equals, it turns out it's the net force on the object divided by the object's mass. Just think about that. At least if you just have one force at a time. If you make the numerator bigger, you get a bigger acceleration, so you get a bigger change. That matches the first point. If you increase the mass, the fraction gets smaller, and the change is smaller. Okay? Oftentimes, this is then rewritten to say, if you just read to the algebra, say the net force, F net, equals the mass times the acceleration. That's fine as well. Questions about this? You guys remember seeing this in high school at some point? Maybe? Some people? No? Okay. So this formula, this is Newton's second law. This is the big workhorse, right? It's the thing that really shows the connection between forces and motion. I mean, the first law is kind of a null result sort of thing. It says what happens if nothing's going on. This is the thing that really shows what forces do to objects. Okay? Forces don't make motion, they make changes to motion. Okay? You don't need a force to have a velocity. You need a force to make a change in velocity, or you need a force to have an acceleration. If an object has no acceleration, turn it around and say there's no net force. If an object has no net force, it will have no acceleration. Does anyone know the name we give to things which have no acceleration or no net force? Those scenarios are called equilibrium. So when something's in equilibrium, there's no net force or no acceleration. Just a vocabulary. It's an easy condition. You set things to zero, but if you don't know what the word means, then you're stuck. That's what that means. Equilibrium means no net force, and the acceleration is zero. All right. Let's take a 5-minute break, and then we're going to go through how to solve. We're going to go through how to solve some force problems. There's a process. I try to model a process that you can take any situation, go through the process, and grind out the answer at the end. It's not the only way to do this. It's not the way I learned to do it, but I find that it helps to have a systematic way for people to deal with it. So let's take a 5-minute break, and then we'll kind of go through some problems as a kind of systematically. And then at the end, we'll go through Newton's third law, and I think that will answer any questions you might have for the whole. Okay. All right. 5-minute break. You can go outside and take your mask off if you want. So I will pause Okay. So, Newton's laws. The way we're going to do this. Sorry. So I should have handed these out. If I have enough. I don't have enough. Shoot. All right, well, I'll just do one on the overhead. You guys will have to, I'll make more copies. Hand these out. Okay, so to use this, we need to look at a situation, assess what are the relevant forces, figure out how to find the net force. That means add them up as vectors, and then use this formula to connect that to an acceleration. So in the simplest problems, you're given all the forces and you have to find the acceleration. Or you could be given the acceleration and asked to find a missing force. Or, there any variation thereof. Okay, so, but in all situations, when you have a force problem, you will need to identify what are the relevant forces and find the net force, the total force, the sum of all the forces. That's always a part of a force problem. So, to do that, we're going to have a device or mnemonic, whatever. It's usually called a force diagram or free body diagram. So, did anybody do that in Physics 1? They talk about force diagrams or free body diagrams, where you draw all the forces in a scenario. Do you remember doing that? Maybe not really. A few people. All right, a little. All right. Okay. So to draw, we're going to make free body diagrams, not out of body diagrams. Free body diagrams. Okay. I'm gonna have like hallucinations and stuff. Okay. So how do we do this? And well, remember, the goal is to find the net force on an object. So, and that's all we care about to use this law. That's the only purpose of a free body diagram. So, we need to put the information. We need to put all the information needed to find the net force and basically nothing else. If we start putting extra pieces of information and we're not careful, we'll end up mixing in things that we shouldn't. And so we don't want to do that. So here are the rules. Try to make this into a procedure. Step 1, draw. Sorry, markers dying. Draw the object as a as a dot. Okay? Newton's laws work for everything. Okay? F net equals ma for everything. So that means none of the details of the object matter to apply this law. So let's not get distracted by details of the shape of the object, the color of the object, the taste of the object. None of that matters, so don't put it in the diagram. We just put a dot to represent the object. If you're being really particular, what it actually represents is the center of mass, or the center of gravity of the object is usually what we mean to represent the dot. Okay, but for us right now, even when things are big, we're kind of ignoring any details about shape. Okay, so you draw a dot. Let's do that. Wow. That could be a cat, a car, a house, or a dot. Draw it the same way. Okay, step 2. You identify all the forces acting on the dot. on, emphasize, on the dot, or on the object. Okay. So if, I don't know, if I walk in, if I'm asking about your motion and your free body diagram, and I walk into a door, does that affect your motion and your free body diagram? No, it's irrelevant. So that would represent forces on me or forces on the door, but it has nothing to do with you. Okay? So that you only include forces which act on that object. Similarly, if you exert a force on someone else, we don't put those forces in your free body diagram. It's only the ones which act on you, not by you. Watch the prepositions. Okay, the free body diagram has forces which act on something, not by it, or not certainly not by someone else or on someone else. Okay? I think it sounds very simple, but it's a frequent problem that people start, there's a force, it's some complicated scenario, and there's a force here, and a force there, a force whatever. And pretty soon, people get so fixated on this force, they start mixing it into all the other diagrams. And it doesn't work that way. Okay? The force acts on one thing, and it only features in that object's free body diagram. It doesn't feature in any other free body diagram in the problem. Okay? All right. So you identify them, and then you draw all forces with I'll draw all the forces with tails on the dot. Now, this last one's not too crucial. If you know what you're doing, you can do it without being so rigid. But sometimes people get a little confused on how to represent something. So if I just have a standard way of doing it, just again, even if it doesn't always matter, having a routine, having a process, making it systematic helps us not waste time worrying about things that don't really matter. Okay? So we have a dot. And what's a common word here in these last two? Other than the and all. Forces. Okay? And what are we trying to construct with this free body diagram? What I say the goal was is to help us calculate the net force. Okay? It's all about forces. So don't put anything in there that's not a force. And the main culprit or the main problem is people start to try to put in acceleration. It doesn't go there. This is just a construct or a diagram to calculate net forces. We don't put anything else in there that isn't helpful. Okay? So let's say I had an object, there it is, and I've got, let's say I've got a force going here, force 1, force 2. Let's say I've got 2 more forces which are parallel, right? They're like going in the same direction. So, right? So I've got 2 more forces that are acting straight down. It is oh so tempting to just use the same arrow and label it like, force 3 and force 4, or something like that, force 3, whatever. Don't do that. Shh, I'm going to erase it before you write it down. Do not do that. There's no shortage of arrows. We can keep drawing them all day. So don't be stingy. Okay, if you've got 2 that are parallel, maybe just displace one a little bit. Just push it over a little bit and call it force 3, and force 4. Okay, so don't try to double up. Why? Well, if you start doubling up arrows, inevitably what will happen is you drop one in the middle of the problem. And then it's all wrong from that point on. So the whole point of this is to do good bookkeeping. So draw the diagram so that you can do good bookkeeping. That's what it's there to do. It's just a bookkeeping device. Okay? Notice, if the forces are at angles, then I draw them at angles. If the forces are perpendicular or parallel, then I draw them that way. I have to make the forces align with what I think they should be. Questions? How to do that? Don't put acceleration in the force diagram. It's not a force. It's all right. Very good. Okay, so once we identify the forces, the goal is to solve this kind of equation. And this is an equation, this is a vector equation, which means it has x components and y components and things like that. So what you're basically always, or hard to say always, but almost always, when I have forces at different angles, I'm going to choose something called x and y, and usually I choose horizontal and vertical. Sometimes I choose for ramp problems, sometimes I choose it differently. It doesn't matter, x and y are my choices. So, but what you're going to do is after you choose what you call x and y, you're going to need to break the vectors into components. Okay, so step 1 is to draw it. Step 2 is trigonometry. Get everything in component form. And even if you can't come up with a numerical, like a number, write it as, using sines and cosines. It might just be a symbolic expression, but so what? That's what it is. All right? And then after you get this far, we'll have a force. So this is a free body diagram. F, B, D, free body diagram. And over here, we're going to have a force table. And I find that this helps people not forget things. So we're going to make a table. And in the table, we're going to go through. And on the first one, we're going to have the forces. And here we're going to have to put the x components. And here we're going to put the y components. So, I don't know. In this case, I have 4 forces. 1, 2, 3, 4. So I'm going to say I have, okay, so force 1, and well, it has an x and a y component, right? So it'd be F1x and F1y. I use sines and cosines if I know that, or I write it as best I can. In this part, I would just put F1x, and over here I put F1y. Let's say I did those. And let's say for 2, let's say I was given the magnitude of F2 and the angle for F2. Maybe, some problems can be written all different ways. So for the force for 2, I would say, okay, in the x direction, that's going to use the cosine of this angle. And it's to the left, because it points to the left, so it's going to be negative F2 cosine theta. And here I would say, well, it's going upwards in the y direction, so it's going to be F2 sine theta. Okay, so I take my free body diagram, I write everything in components, and I just start filling in x component of this, x component of that, blah, 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 blah. The nice thing about putting it in a table is if you forget something, you have a big hole in your table. If something is 0, we'll write a 0. So that when it's all done, you've dealt with everything because everything's filled in. So for example, forces 3 and 4, I don't know what, whatever, I didn't give numbers. But what I do know is they're going straight down. So I put zeros here. And I just say F3 and F4. I put in the because it points only in the vertical direction, the y direction. Okay, so again, you don't have to do this, but I strongly suggest you do this just because it becomes systematic. It just is a bookkeeping device so you don't forget anything. If you forget something, it shows up, it's obvious, right? It did everything else, I missed one step, put it in. When you're done, remember, vector addition, because we want the net force, and for vector addition, that's just normal addition on the x pieces, the x components, and normal addition on the y components. That means when we're going to construct the net force, you just add up, you just add these up. You just add up the column. You add them all up. Oh, that was that. That's 3. So you just add column. Okay? And then this would become the x component of the net force. And this would become the y component of the net force. It's just doing what we were doing with vector addition, but just putting it in a table so we don't forget anything or we don't lose anything. It's the same idea. And so then this number, for example, would give me F net in the x direction, and I could set that using the second law equal to the mass times the acceleration in the x direction. And this number would equal F net in the y direction, and that would equal the mass times the acceleration in the y direction. Okay. So making a free body diagram and a force table, the free body diagram is pretty much a must. The force table, that's not something, when I took Physics 1, we didn't do that, but I have found that organizing it that way seems to help people remember everything. So I would encourage you to do that. If there's a problem about forces, there's basically always going to be some sort of free body diagram. So that means partial credit, right? Even if you don't know what to do this. Even if you don't know what to do, try to do this, right? And you're at least going to get a few points here and there, here and there, here and there. And over the course of the semester, that adds up. So if there's a problem with forces and you don't know what to do and you just can't solve it, fine, it happens. But you can try to do this. You can at least indicate that you know stuff, stuff and the basic idea, and that you kind of have a process you're trying to grind through and get an answer. These are the kinds of things you would want to make sure every problem has. Well, even if you can't finish it, do that much. All right, I'm running out of time. All right, let's do a simple problem. And then we'll talk about the third law for the sapling question. Okay. Oh, one thing, I was going to do a problem with weight, but I think we won't have it. The formula for the force of gravity or weight on any object is equal to, so the weight of an object is minus the mass times the gravitational acceleration. This isn't times, I'm going to write y hat, because it goes in the y direction, where y is up and down. It's really the vertical direction. Sometimes people say they just call little g gravity. But now we have gravity as an acceleration and gravity as a force. So you have to be more particular. Weight is the force of gravity. G is the acceleration due to gravity. And what was it? Is that the force of gravity? Is G the force of gravity? No, it's the acceleration of gravity. What is the thing that you never put in a free body diagram? Acceleration. So should you put G in the free body diagram? No. G. So G is the acceleration due to gravity. It doesn't go in a free body diagram. The weight is the force of gravity. Ding, ding, ding. That's what goes in the free body diagram. So in a free body diagram, you put weight, you don't put G. What happens is people put the weight and they put G. That's kind of like over-counting gravity. You kind of got it, its effect and its cause, double count it in the same free body diagram. Don't do that. Okay. All right, so I'm going to set that aside. We'll do more examples with that later. But let's do a problem. There is a very stubborn student being pulled in different directions. Okay. We are told that this force goes straight down. And let's say this is 10 newtons. Oh, the unit for force is a newton. 1 newton equals 1 kilogram meter per second squared. So 10 newtons straight down. This force is going to be 20 newtons. No, I need to make this bigger. I'm sorry. Let's make this 30 newtons straight down. Sorry. This will be 20 newtons at 30 degrees above the x-axis. And then we have another force, we'll call it T3, some other rope, and it goes at has some magnitude and some angle. All right, so that's the scenario. People are pulling on each other in different directions. The person, because they're stubborn, the person's not moving. They're stationary. Something's stationary. What's that code word for? It's not moving. It's not moving.
At rest.
At rest, yeah. Does that mean I could set something to 0? What could I say is 0 if it's at rest? Certainly the velocity is 0. If it's not moving, the velocity is 0. But if it's 0 and not changing, it stays 0, 0, 0, 0, 0. The velocity is 0, and what else is 0? Acceleration. So both, for this person, both the velocity and the acceleration are going to be 0. If the acceleration is 0, what does that tell you about the net force? The acceleration is 0. What does that tell you about the net force? F net equals mass times acceleration. F net equals ma. If the acceleration is 0, then the net force is 0. Which means when I go through this construct, whatever fits right there must equal 0. And whatever fits right here must equal 0. For people who've started the homework, I think this is pretty much homework question 1. One of the, maybe 2, or one of the homework questions is like a donkey and people are pulling out in different directions. It's this problem. Okay? Let's go through this. So the goal is to find T3. So find T3 in the x direction, T3 in the y direction, and then just for fun, let's find the magnitude of T3. And let's find this angle, theta. So let's find all of these things. Okay, but really, the problem is just to find these, and then this is just trigonometry. Okay, so here's the scenario. I've almost given it to you as a free body diagram, but just go through the process. So there's the scenario. Go through the process. Draw the free body diagram. Construct the force table. Fill in the pieces. And then once you have that, then you kind of have to use logic to get to the answer. All right, so I pretty much have my free body diagram, so I'm not going to redraw it. It's just basically the story it gave to me. What I do want to do, though, is work things out in components, component form. So I'm going to use X and Y. I'm going to choose X to be horizontal and Y to be vertical. There are some problems where that's not the simplest. The math is easier if you choose something differently. And I'll talk about how to do that when we get there. But if I do that, I work things out vertical and horizontal, I know that to fill in this table, I'm going to need the X and Y components. So I want to think of these as triangles. And the adjacent side to this 30-degree angle is the X component. So it's going to be, if I'm naming these 1, 2, and 3, then I'm going to say the tension for rope 2 in the X direction is 20 cosine 30. And the cosine of 30 is 0.866 times 2 is 1.7 something times 10. So it's going to be, it's going to be, 17 point something, 17 point, what do you get for somebody who did it? 3.2. Okay? Fine. And it would be newtons. We're being really careful with units. For the y component, that's going to be T2y, T2 in the y direction, and that's going to be 20 sine of 30. Sine of 30 is a half, so that's going to be 10 newtons. Good so far? Everybody did? Okay. So for every vector, you're going to have to, if it's at angles, you're going to have to do trigonometry on it each time. So if you see things at angles, immediately, trigonometry. Just got to know that. This one is only in the y direction. So you just say that that is 0x component, and the y component is negative 30. For T3, I don't know anything about T3. That's okay, because that's how we're going to work in. Remember, this is what we're trying to find. We're going to work this stuff into the mix. What I do know, though, is that I can say, oh, okay. This part would be T3x, whatever that is, that's where it would go. And this part would be T3y. Okay. Questions on that? Now, when I put things into the, you got to watch the minus signs. You don't want to overcook them. If you're going to be wrong on a minus sign, be wrong twice, I guess. So on this one, T3, this vector is going to the left. So I'm expecting this answer, when I'm all done, to be negative. Just visually, it has to be. So I'm not going to assume anything. I'm just going to put it in the equation. I'm going to do the algebra, and I'm going to just let algebra tell me positive, negative, whatever. But I know if I've done it right, it'll come out negative. Little things like that are good checks. That you got the minus signs right, and you just understood the problem. Okay, so I've got all my stuff, my vectors drawn. I figured out components. Now I just put it into a table. So I've got forces, X, Y. I've got tension 1, tension 2, tension 3. And then over here I'll have net force. Okay. Tension 1 in the X direction. What should I write down? Here. Tension 1 in the X direction. What do I get from the diagram? 0. This rope doesn't go in the X direction at all, so it just gives 0 result. But I need to write 0. If you leave it empty, you think you didn't do something. So I write 0 when I know it's 0. And then I get negative 30 newtons in the Y direction. For the second rope, T2 in the x direction, we said it was 17.32. And usually before I proceed, I worry about minuses, and I know the mistakes I make. So I make one last glance, say, oh yeah, it was to the right in the x direction, so plus, positive, it's good. In the y direction, I get positive 10 newtons. It's going upwards, makes sense. For T3, I don't know either. Well, that's okay, I just put it in T3x and T3y. It is whatever it is. That's the point of the problem, to figure that out. How many people made it this far? Okay. So get to this point. Now, this is the net force. You just add them up down the column. So this is going to be T3x plus 17.32. Newtons are getting squeezed out, but it's there too. And here, I get T3y, and I get plus 10 minus 30. That's T3y minus 20. Just adding things up down the column. So I just pull it out here. I'm just going to pull this out of the table, and I get the net force in the x direction is T3x plus 17.32, and the net force in the y direction is T3y minus 20 newtons. Awesome. That's the result. I just pull out the pieces. Now, what can I say? So really, I'm just in trigonometry. I haven't done any physics. The physics comes at this point. This is where the physics is, right? That's the content of Newton's second law. And until you use it, you haven't done any physics. We say that the net force in the x direction is the mass times acceleration in the x direction. What is this person's acceleration in the x direction? What do we say? Is it moving? Is this person moving? No. And they're stationary. Their velocity is not changing either. The acceleration is 0 in the x and y. So the acceleration is 0. Therefore, this net force in the x direction must be 0. If the acceleration is 0, we get 0. And we get it for both x and y. Now I have two equations and two unknowns. It's just algebra. It's just math at that point. And I learned just from solving that equation that T3 in the x direction is negative 17.32, and I'll go ahead and put it in newtons. T3 in the y direction is positive 20 newtons. Now, let's stop. Check. Does it match our intuition? Does it seem right? The x component is negative. Yes, because this arrow is going to the left in the x direction. The y component is positive. Does that seem right? Yes. It's really easy to have an extra minus sign, and then you get the arrows flipped, and then it's all garbage. So before proceeding, try to look at it. Do one last check. Seems good. I think I understand the problem. I feel okay with it. I just assume it's right. And move on to the next thing. Okay? How many people got this far? You got the x component. Okay. If you didn't get it, do you see how to do it? Next, if I gave you the problem again, could you do it? Okay. Like, if I gave you the problem again tonight, WhatsApp, like, maybe call the student a donkey. Could you do it? It's really the same thing. I think on that one, I think it's basically the same. Maybe it's not 30 degrees, but it's really the same idea. Okay. Oh, if anyone's done that, do they ask for the angle with respect to the x-axis? The the positive x. Okay, so that would be something. All right, let's go through. We know these two numbers. How do we find T3? Magnitude. How do you find the hypotenuse of a triangle? You know the horizontal, the base and the height. Use some theorem. You use the Pythagorean theorem. So you're going to say the magnitude of T3 is the square root of 20 squared plus 17.32 squared. 26 or something. I don't know. What do you get? 26.46. Sure. That's the magnitude. Now, this angle, as I defined it, is an angle less than 90 because it's not defined in the math. For mathematicians, would you want the angle back to the positive x-axis? So let's find this angle, and then maybe on sapling they want you to take the supplement, take 180 minus the answer. So, anyways, let's find theta. How could you find theta? Well, I would do the inverse tangent of this component over that component, and I know the answer is going to be between 0 and 90, so I just work with magnitudes. So I would do, say that theta is inverse tan of y over x, so that's going to be 20 over 17.32. I'm not worried about minus signs because I know the answer of, I know that I want the positive answer between 0 and 90, so I don't worry about it. If you're not sure, then you can be more particular and more careful. Okay. And this ratio is bigger than 1, which means tangent 45 equals 1. So I want an angle a little bit bigger than 45, so I don't know, let's say 50, 40. Plus change, right? There'd be other digits there, but that's a rounded number. Yeah, that feels right. Qualitatively, just that warm feeling. You don't get that when you guys do math? No? That warm, fuzzy feeling feels right. Okay, so that's 49 degrees, the answer for that. And maybe on sapling, what they want, I don't remember, they might want this, the bigger angle, so you do 180 minus that to get the answer they want. You always have to do that with saplings. Get your answer and rework it into that. Okay. In 2 minutes. Newton's third law. I'll say this again on Tuesday. Newton's third law says for every force, some people remember here it as for every action or for every force, there's an equal and opposite reaction force. I don't like to say it that way because I can never remember what's the action, what's the reaction. It's like, I don't know. Here's what we'll say. For every force I exert on something, there's an equal force back on me. So one of the forces is from the object, the other force is on the object. From and on. Watch the prepositions. Okay, it's all about prepositions. By the object or on the object. So, and they are equal and opposite. And sometimes people say, well, wait a minute, how does that mean? How does anything ever happen? If all the forces are equal and opposite, why don't they just add it to 0 and nothing happens? The key is the preposition. Between two objects, you and me, the forces between us would cancel. But when we study the free body diagram, we don't include all the forces. We only include half of them. We only include the ones acting on something, not by. So that's why it doesn't cancel out. Because you're not, right? If you included all the pairs, action-reaction pairs, yeah, they'd all go to 0. But that's also not the right thing. You're not supposed to do that. The acceleration of an object is determined by the forces on it, not by it. Okay. In the homework problem, it's all about language. They've got like a car pulling a trailer, blah, 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 blah. They want you to identify action forces and reaction forces. And in the paragraph, they tell you what they mean by action forces and what they mean by reaction forces. Go with what they say. The key is, though, the preposition. If it says on the car, right? So it'll say, like, I think it says action forces are by the car, reaction forces are on the car. And they'll give you a list of like 10 different forces. Look for the preposition. If it says on the car, then it's a reaction force. And if it says by the car, it's an action force. It's really that simple. You just go through the list and look for on, by, on, by, on, or by. That determines the answer. Okay, so, and then if there's something which is not a force, then it shouldn't be included. So if they give you an acceleration, that's not in the list. Okay, so they're trying to trick you. Okay, so it's really that simple. Watch the prepositions. And they tell you in the paragraph what they mean by action, reaction. So just go with what they say. I think what I said is right, but I always get confused. In formula, in math formula, the third law will say, we'll say force of one thing on the other. So A on B equals minus the force of B on A. So we'll put subscripts. Do this next week. Subscripts will indicate what causes the force, what feels the force. A on B. And Newton's third law says if for every force of one thing on another, there's an equal and opposite reaction force going the other way. A on B is minus B on A. Right? So next week we'll do that. But that's what you should do. Okay. All right, let's stop there. People online, you doing okay? They're asleep. Oh, Gavin's awake. Okay. Freya's, she's gone. I don't blame her. Okay, I'll see you guys. Next week we will be online all week. So on Tuesday, let's think about this. On Tuesday, we have the exam. On the next homework is going to be due on next Friday. And we will have online class during this time block on Thursday. Okay? All right. See you guys.